Everybody? Alright, today I'm going to be teaching you guys how I would think about and how I personally would do EAS and NAS reactions, because I think that's what you guys either just learned about or currently are working on. So that's what this is going to be. I've done this once before, this screen record bullshit, so I'm not like the most technically proficient at it, but just bear with me. So today we are going to be doing EAS and NAS. Alright, and essentially, the way that you guys should think about that is we are going to be learning the mechanisms and the how-to for putting shit on benzene. It's essentially what all of these reactions more or less are going to boil down to, okay? And so, for example, if I have a molecule of benzene and I want to turn that molecule into bromobenzene, or maybe I want to turn it into ethyl benzene, or maybe I want to turn it into acetyl benzene. Okay, we're going to learn how to do all of these manipulations. So we're going to start with benzene, or a derivative of benzene, and we're going to learn how to add stuff to that benzene ring. Okay, that is the crux of what we're going to be doing. Okay. So before we actually do any of that, we need to talk about the fact that benzene is a certain class of molecules called aromatic molecules. Okay, so we need to talk about what makes benzene aromatic, and in general what makes anything aromatic. Okay, so in order for something to be aromatic, there has to be 3 criteria that it satisfies. Okay, so something has to be completely cyclic. Okay, so non-linear. Okay, and when I say it has to be cyclic, it can be any number of atoms in the ring. So for example, you can have a 3-membered ring, which would be a triangle. You could have a 4-membered ring, which would be a square. You can have a 5-membered ring. You could have the classic 6-membered ring. You could have a 7-membered ring. You could have an 8-membered ring. Okay, yada yada, you get the point. All of these would be cyclic. Also, when we're talking about molecules as a whole, sometimes we say that the molecule is aromatic. It just means that it has an aromatic portion in it. So, for instance, something like this, right, that would still be considered aromatic because it has an aromatic portion in it right there. Obviously, the propyl group is not cyclic, but that's what we mean by cyclic. There has to be some sort of cycle. Okay, so that is the first criteria. The second criteria, okay, is that every atom must, and this is a very, very, very important must, every single atom must be, all right, sp2 or sp hybridized. Okay. Or if you are sp3 hybridized, okay, you have to have a lone pair. You have to have a lone pair that's adjacent to a pi bond. Okay. So let's talk about what I mean by that. Okay. So we know that it has to be cyclic. So let's draw a nice 6-membered ring here. Okay. Now everything has to be sp2 or sp hybridized, or it has to have a lone pair that's adjacent to a pi bond. So let's say I put like a double bond here and a double bond there. Okay. Obviously, because this carbon has a double bond, and this, I'll make it a different color, because that one has a double bond, and that one has a double bond, and that one has a double bond, and that one has a double bond. All of those carbons are sp2 hybridized. But hopefully what you guys can see is that this carbon is sp3, and this carbon right here is also sp3, and so therefore this system would not meet the criteria of aromaticity. If we wanted to make this aromatic, possibly, without actually introducing any more double bonds, right? Okay. Like I said, right, you can have a lone pair that's adjacent to a pi bond. So if I put a lone pair here, right, and I also put a lone pair here, okay, then it would at least fit criteria number 2. Because now every single atom is sp2. So the yellow atoms are sp2 hybridized. And these purple atoms right there and there, technically those are sp3, but they have a lone pair that's adjacent to a pi bond. Okay. And the main area that you'll see that little exception run into, most of the time that exception occurs with nitrogen and oxygen. So for example, you'll have a molecule like this. Okay. And that molecule is called furan, and furan is aromatic, okay? Because this carbon is sp2, 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 and it looks like the oxygen is sp3, but that oxygen has a lone pair that is adjacent to a pi bond, okay? You could also do the same thing if you have a molecule if you have a molecule that maybe looks something like this. Oh, shit. Let's put a nitrogen right there. Alright. Okay, so if you have a molecule like this, obviously these 4 carbon atoms are sp2 because they have a double bond. This lone pair is adjacent to that double bond, and this carbon atom is sp2 hybridized because it's positively charged. So if you guys didn't know that, anytime you have, so if you have a positive or a negatively charged carbon, those are always, well, not always, but in this class, they are sp2 hybridized. So any positive or negative carbon, you just know for a fact right away that that thing is going to be sp2 hybridized. And again, this lone pair on the nitrogen, okay, that lone pair is adjacent to a pi bond, so therefore that whole system would be conjugated. All right. So by the way, that is what this whole thing means. So when every single atom is sp2 or sp hybridized or has a lone pair that's adjacent to a pi bond, we call that conjugated. Right? So that's what we mean when we say conjugated. Okay. So the final criteria is that the total number of pi, which really just means conjugated, the total number of pi electrons, okay, is 4n plus 2, where n equals a positive integer or 0. So n can equal 0, 1, 2, 3, blah, blah, blah. Which means that the number of pi electrons, in order for something to be aromatic, has to be 2 or 6 or 10 or 14, yada, yada, yada. Okay. Okay, so knowing all of that, let's draw some aromatic molecules. So okay, if I had this would be aromatic, and hopefully you guys can see that that's aromatic because this thing is cyclic. Obviously it's a triangle. All of the atoms are sp2 hybridized, so this atom and this atom is sp2 because it has a double bond, and this carbon is sp2 because it's positive. And the total number of pi electrons, the double bond has 2 electrons, and the carbocation has 0. Okay, so just to clarify, if you see a carbocation, that counts as 0 pi electrons. If you see a pi bond, that counts as 2 pi electrons. If you see a lone pair, that counts as 2 pi electrons. And if you see multiple, so multiple lone pairs, that also only counts as 2 pi electrons. Also, if you have a lone pair and a pi bond, once again, that only counts as 2 pi electrons. Alright? So, right? So we already said that this molecule right here, so this was aromatic. Okay, but if I would have had this molecule right here, okay, this thing would not be aromatic. Alright, and this has a special name. I haven't taught that to you yet. If you guys have hopefully read the book, you'll know what that is. But this thing would not be aromatic. This thing is not aromatic. Okay, and it's not aromatic because it is cyclic, and every single atom is sp2 hybridized, but it doesn't have 4n plus 2 pi electrons. Okay, so let's do some more aromatic molecules. So we just did a 3-membered ring. Let's do a 4-membered ring. Okay, okay, a four-membered ring is going to be a little bit difficult to make it aromatic, but you can imagine if we have 2 there, then sort of as silly as this looks, we could do something like this. Okay, so this would be aromatic. 1, 2, 3, 4, 5, 6. Yep. Okay, so this would be aromatic again because it is cyclic. Okay, all of the atoms are sp2 hybridized, and there would be a total of 6 pi electrons here. Let's see if I make it with like oxygen. Let's see. So I could put like maybe, I'll put like a double bond there. I'll put a lone pair here. Okay, I could also maybe do something like this, right? Okay, 1, 2, 3, 4. Yep. So this molecule right here would also be aromatic. So obviously this molecule is cyclic. So all carbons are sp2, and the oxygen lone pair can resonate. So being able to resonate means it's adjacent to a pi bond. They go hand in hand. All right, and then obviously if we count again, right, we would have 1, 2, 3, 4, 5, 6. So there would be 6 pi electrons here. So that molecule, I've now kind of written all over it, but again, I know it looks kind of silly, but that molecule right there would also be aromatic. Okay. All right, if we want to go to a 5-membered ring, we already did that one. We already did an example of that one, right? So something like this molecule would be aromatic. Okay. Again, obviously this thing is cyclic. Okay. The carbons are all sp2, and the oxygen lone pair can resonate. And then the total number is 6 pi electrons. Okay. All right. Okay. So if you guys go on Google, you probably can literally search for like aromaticity problems if it confuses you. There's probably a lot of practice problems that you can do, but those are the rules. Okay. So that is aromaticity. All right. So aromaticity, cyclic, sp2 or resonant capable, and 4n plus 2 pi electrons. Okay. Now it turns out that there's something that's very closely related to aromaticity, that is called anti-aromaticity. And anti-aromaticity are things that are also cyclic. And they are also all sp2 and or resonant capable. Every atom is sp2 or resonant capable. But now, the only difference between anti-aromatic compounds and aromatic compounds is that they have 4n pi electrons. Right? So, for example, if I just have a 4-membered ring that is fully conjugated with double bonds, that is an anti-aromatic molecule. And that is anti-aromatic because it is cyclic. Obviously, it's a square. All of the carbons are sp2. sp2 on all carbons. But there's only 4 pi electrons, and obviously 4 pi electrons is 4n, where n is equal to 1. So that would be anti-aromatic. Right? Okay. And again, I don't want to spend too much time belaboring this point, but something like maybe okay. So that compound, if it were to exist, would also be anti-aromatic. And this compound this one would also be anti-aromatic. All right. So hopefully that makes sense. All right. So that is how, first of all, to know if something is aromatic or not. So of all of the aromatic molecules, the one that you will encounter most often and the one that is by far the most important is a 6-membered aromatic compound that looks like this, and it is called benzene. And in fact, benzene is so important and so ubiquitous that we are going to spend the entirety of this video talking about how to add shit and how to manipulate a benzene ring. Okay, so before we talk about how to add stuff to benzene, we have to talk about sort of the nomenclature of benzene and just getting to know benzene and being familiar with it. So benzene has some very specific nomenclature that's associated with it. All right. So let's talk about the nomenclature of benzene first. So benzene looks like this. If I have a substituent on benzene, let's say I have a methyl group right here, okay? Let's say I then have a second substituent on there, okay? That second substituent, let's say that second substituent is a bromine atom, okay? Now if you think about it, I could put that bromine atom immediately to the left of that benzene. I could put the bromine atom 2 carbons away from the original substituent, or I could put it the maximum distance away from that original substituent. Okay, and hopefully you can see that all 3 of those molecules would be different. Okay, so we have specific names for these molecules. And specifically, we're not going to name the whole molecule, but I want to talk about the different places that the bromine atom is. So we call the bromine atom at the top, we would say that that is in the ortho position. And I'll explain what these mean in a little bit. We would say that the middle one is called the meta position. And the one where the bromine is completely opposite the initial substituent, we would call that one the para position. Okay. All right. Now the important thing to know about all of these positions is that ortho, meta, and para They are relative. They are not absolute. Okay? They're relative. They're not absolute. And what that means is that it makes no sense to say that I'm going to attach a chlorine in the meta position, because there is no such thing as the meta position of a benzene ring. You have to say that you're attaching the chlorine meta to something else. Okay? So for example, all right, if I have a benzene ring, let's say I have a benzene and I have a methyl group right here. Okay? So the proper name for this would be methylbenzene. This has a common name called toluene, but that's not really important for now. This is methylbenzene. So if this is methylbenzene, so if methylbenzene is right here, the ortho positions are the ones that are immediately adjacent. So ortho is immediately adjacent. Okay? So the ortho position is the position that's immediately adjacent. The para position is the position that is opposite. Para is opposite. And then the meta positions are in between ortho and para. Meta meaning middle, they're in the middle. So the meta is in between ortho and para. Okay? So hopefully you guys can see, right? In methylbenzene, if I orient my methylbenzene that specific way, then the ortho would be where the yellows are, the meta would be where the greens are, and the pink would be para. Okay? But obviously, if I would have put my methylbenzene, if I would have drawn it like this, then now the orthos are right here, the para would be right here, and the two meta positions would be right here. Okay? Right, so in this example, right, in the top example, the top carbon is an ortho group, and in the bottom one, it's a para group. Again, that's because ortho, meta, and para are not absolute. They are relative, right? So we talk about something is ortho to something else. Something is para to something else. Nothing is just para on its own. That would not make sense. Okay? So that is how you talk about ortho, meta, and para positions of a benzene ring. And then there's one other nomenclature thing that I want to get out of the way. So when you have benzene and you have alkyl groups coming off of the benzene ring, okay, we have a specific way of naming whether or not something is on the alkyl group or whether it's on the ring itself. So any carbon that is on the benzene ring itself, okay, those are called phenylic carbons. And the specific carbon that is adjacent to the benzene ring, okay, that is called the benzylic carbon. So it's a little bit of a misnomer because the benzylic carbon is not actually on the benzene ring, but the benzylic carbon is one over from the benzene ring. The benzylic carbon is adjacent to the ring, and the carbons that are physically on the ring, they are called phenylic carbons. Okay. So hopefully that makes sense. Alright, so now we've talked about the nomenclature a bit. Let's talk about the structure of benzene. So benzene looks pretty simple, and it is, okay? Alright. So when you draw benzene, it looks like this. But one thing that you might notice is that you can draw a sort of a never-ending resonance structure with benzene, where that could go there, that could go there, and that could go there. And if you do that, then you would get the bonds moving around. And you would get that, okay? So hopefully what you can see is that in reality, the double bonds at all points are sort of all over the place in the molecule, and that is why you will sometimes see benzene as being drawn with just a circle, representing that every single carbon atom sort of has like a partial double bond character, okay? And because of that, benzene, okay, right, and if we draw benzene sort of the normal way, like this, all right, you will notice that every single carbon atom is sp2 hybridized. And remember that when you are sp2 hybridized, it means that you have an empty p orbital, okay? Well, it doesn't have to be empty, but you have a leftover p orbital. So all of those yellow carbon atoms are sp2 hybridized. So when you have a benzene ring, right, you have the sigma bonds, which are what I've drawn, and then you have all of these p orbitals. And because benzene is perfectly flat, all of those p orbitals that I've just drawn are in the same plane. And because they're in the same plane, all of these lobes perfectly line up with one another. And because they perfectly line up with one another, the electrons in that pi bond framework can simply swim around in this giant loop of p orbitals. Okay, and that is why we get structures that look like this. Okay, where the electrons are simply just swimming around and around the benzene ring. Okay, right? And it turns out that that actually makes benzene incredibly stable. Okay, very, very, very stable. Right? But to really understand why benzene is stable, then we actually have to draw not just the atomic orbitals like I drew there, but we need to talk about the molecular orbitals of benzene. So let's talk about molecular orbitals of benzene. Okay. All right. So the way to show the molecular orbitals of benzene, or really the molecular orbitals of any cyclic conjugated system, aromatic or anti-aromatic, is we're going to draw a Frost circle. Okay, so draw a Frost circle. Yeehaw. Okay. So, what is a Frost circle? So we have to talk about what the hell a Frost circle is. A Frost circle is going to help you figure out where the molecular orbital energies are. A Frost circle doesn't tell you what the orbitals look like, but it tells you how energetic they are. And that's going to be very, very important to explaining the stability of something like benzene. So when you're drawing a Frost circle, the first thing that you're going to do is draw a circle. That's pretty easy, right? Hopefully everyone can draw a circle, okay? And then what you're going to do is you are going to insert the shape of the ring into that circle. Alright, blah, blah, blah. Such that it is resting on a point. Okay, so it's such that it's resting on a point. It cannot be flat, so we're not resting flat. Okay, so before I get into part 3, let's just do the first two. So let's say you were asked, right? So draw a Frost circle for benzene. Actually, let's start simpler. Draw a Frost circle for that thing, right? So we already talked about the fact that this compound would be anti-aromatic, all right? So let's draw a Frost circle for it. So the first thing I'm going to do is draw a circle, okay? And then what I have to do is I have to place the shape. So I'm not worried about the double bonds or anything. I'm just placing the shape of the ring itself, which is a square. So I have to place a square inside the ring such that it is resting on a point rather than flat. So what I mean by that is I'm going to put it in the ring like this. Okay, I have to rotate it. right? All right. Because if I put it in normally, like a normal square, then hopefully you guys can see it would be resting flat, right? So this would be resting flat, and it cannot be resting flat. It has to be resting on a singular point. All right. So this would be incorrect, but this would be correct. All right. So let's see if we can draw. Oh shit! I made this thing so big. All right. Whatever. All right, so let's see if we can draw a frost circle for benzene. So if we draw a frost circle for benzene, we're going to start by drawing a giant circle. Okay. And I then have to put in benzene, but I need to make sure that the bottom of benzene is a point rather than flat. So some people sometimes will draw benzene like this. But obviously the bottom here is flat, so that's not going to work. So the other way to draw benzene is to draw it like this, where you rotate it a little bit, so now the bottom is a point. And now that the bottom is a point, now I can actually put this in my frost circle. So I'm going to make the point right here. All right, so... All right. And then I can put in my double bonds if I really want to. All right, but hopefully you guys can see that would be the frost circle for benzene. And now, the final thing that the frost circle enables you to do, okay, or enables you to sort of think about, right? So the points of intersection. So the points of intersection between the circle and the ring are the energy levels of the MOs in the molecule. Okay? And the center of the circle is where energy is equal to 0. Alright? Alright, so what does all of that mean? So it means that if I gave you the question and I said draw the molecular orbital energy levels of benzene, right, how would you do that? So you would do it by doing a frost circle. So I draw my circle. Alright. Once I draw my circle, I know that I have to orient my benzene so that it is resting on a point. Like that. And then once I do that, then I know that my energy levels are going to be where my circle and my benzene level atom meet, which means they're going to be here, 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 and this is a little bit lopsided. And then I know that the 0 energy line is going to be right in the center of the circle. So it's going to be there. So all I would have to do is take this image and just translate it to an actual energy diagram thingy. So if I have energy on the x-axis and I put 0 right here with a nice dotted line, then I know that in benzene there's going to be 1 molecular orbital on the bottom, and then there's going to be 2, looks like they're about here and here, and then there's going to be 2 maybe like there and there, and 1 right up at the top. Alright? So this would be the energy levels of the molecular orbitals of benzene. Right? Okay, so the energy levels of benzenes, molecular orbitals. Shit. Of benzenes MOs. Okay. Shit. All right. Perfect. Good. So now, actually, we'll do like one more. So let's see if we can figure out. So if I ask you to draw the energy level diagram. For the molecular orbitals of this thing, let's do THF. Or sorry, not THF, just furan, this molecule. Alright? Alright? So again, we're going to start by drawing a circle, a frost circle. Alright? And now we're going to inscribe the shape of the aromatic ring. Again, it doesn't matter where the double bonds are in the ring. It doesn't matter if I have a heteroatom. It's just the shape. So in this case, it's a 5-membered ring, so I'm going to be inserting a pentagon. And hopefully, if you notice that in order for me to insert this pentagon into that circle where it's resting on a point, I'm going to basically have to take the molecule and flip it upside down so that it would be like right there. So it's going to look like that, and then maybe that, and then that, and then that, and then that. Maybe? Okay. Alright, perfect. And then I know that my 0 energy line is going to be like around right there-ish. Okay. So again, right, I would put my energy on this axis, and I know that my 0 energy line is going to be right about here. Okay. And it looks like in furan, I would have 1 orbital on the very bottom, and then I would have 2 orbitals that are very, very, very close. Actually, it looks like they're exactly on the energy equals 0 line. Right. And then I would have 2 orbitals that are above the energy equals 0 line. Okay. So this would be the energy levels for the MOs of furan. Okay? Hopefully that makes sense. Alright? Alright, good. So, now, once we know that, then we can actually fill in, right? So, let's talk about what makes an aromatic compound like benzene so stable. So that's what benzene looks like, right? So benzene has 6 pi electrons, right? And I know that the energy level of benzene, right, of the molecular orbitals, right, based on my frost circle, I know that it looks something like this, okay? And because it has 6 pi electrons, when I go to fill in this diagram, I know that I'm going to have to fill it in like this, right? So 1, 2, 3, 4, 5, 6, right? So if you notice, all of benzene's electrons are in orbitals that are much lower than the 0 energy, meaning they're in very, very stable orbitals, right? These orbitals are all much lower, so much lower than the 0 energy, meaning they are very stable. Ah, shit. Okay. Damn. My pen's going dumb on me here. Okay. They're very stable. Alright. Alright. But if you look at something like this guy, right? remember the Frost circle for those molecular orbitals. Um, The Frost circle for this one, because this only has 4 electrons in it, would look like 1, 2, 3, 4, right? And obviously, so not only does this have, so this is bad for 2 reasons. One, this has 2 electrons in a fairly high energy orbitals, right? Because in benzene, all of the electrons, every single one of them, hopefully you can see this, all of the electrons in benzene were in orbitals that were lower than the 0 energy line. But now, literally half of my electrons are in orbitals that are on that energy line. So it's higher energy anyway. But even more so than that, 2 electrons are unpaired. Okay? And in chemistry, you don't see a lot of unpaired electrons. And the reason you don't see a lot of unpaired electrons is because unpaired electrons are extremely unstable. Right? 2 electrons are unpaired, and what that means is that when you have anti-aromatic compounds, you're dealing with a diradical. Radicals are not stable. Diradicals are extremely, extremely not stable. And so this whole thing is an absolute mess. And that is what makes anti-aromatic compounds very, very, very bad. Okay? And essentially not very fun to deal with. Okay? Alright. So the last thing about structure before we can move on to more fun stuff, in my opinion, more fun stuff. Okay. So Frost circles allow you to know where the energy level placements of benzene's molecular orbitals are. So if I have benzene, I know that the molecular orbitals are here. I know that there's 2 degenerates, and then I know that there's the 0 energy line, and then I have my unstable orbitals up here. Okay, so, and then this is energy on this axis. So the Frost circle allows me to take a molecule like benzene in the yellow and translate that to a picture like the blue. But it doesn't actually show me what those orbitals look like. So to do that, you actually are going to use the same exact rules and the same exact logic that you guys used when you were drawing the molecular orbitals of linear systems. And they're not that much different when you apply them to benzene. Okay. So the first orbital is always going to be the easiest. The first and the last is always going to be the easiest. The first orbital is going to be the easiest because you guys know that there's no nodes in the first orbital. So every single lobe gets shaded the exact same way. Alright? So, by the way, when we're talking about the molecular orbitals of these conjugated systems, we use the Greek symbol psi. Okay? So I would call this psi 1. So psi 1 is going to be, actually, this one would actually be a phi. So, hold on. I got my Greek letters mixed up. Psi. So that would be psi 1. Right? So psi 1, okay, the lowest energy, right, is always going to have 0 nodes. Just like if you guys remember when you did molecular orbitals for linear systems, right? The way that you did that was you made it symmetric and you made sure that the number of nodes increased from 0 to 1 to 2 as you went up and up, okay? So psi 1 is going to be easy because it has no nodes and therefore you know that you just have to make it, every single shading is exactly the same. So now what I have to do is I have to figure out how I can shade this such that it is symmetric, but that there is one node. And when you're dealing with linear, non-conjugated, conjugated, but non-cyclic systems, then the node is simply like a nodal point. But here, we have to think about nodal lines, right? So there's going to be an entire line that cuts across the benzene ring, all right? So if you think about it, a really easy way to make a nodal line would be to have a nodal line that cuts the benzene ring right in half, like this. And in order for me to do that, I would shade these on the top half, and I would shade these on the bottom half. And hopefully you guys can all see that that would in fact be symmetric, and it would in fact only have one nodal line. So this would be psi 2a. But hopefully what you guys can see is that there's actually another way to make this symmetric and only have one nodal line, and that would be if my nodal line went right down the center. So if my nodal line went like this. And in order for that to be the case, then I would shade this one and this one up top, but these two down on the bottom. Okay. And that one still only has one nodal line. Right? And that is why you have these two degenerate energy levels, because there are two ways that you can get one nodal line. And because they each only have one nodal line, they're the same exact energy. So you have psi 2a and psi 2b with one node. Okay? And really, again, it's a nodal line, right? All right. All right, so if we want to keep doing this, let's see if we can figure out what psi 3a and psi 3b look like. So now I need to figure out how I make this thing symmetric while including two nodal lines. And if you guys want to think about it for a little bit, I guess you can pause this video. But if you are ready to figure out the answer, I'm going to spoil it for you. So the way to make two nodal lines here is you can put one nodal line like this, and you can put a second nodal line like that. All right? And hopefully when you guys do that, you can see that molecule is still symmetric. The nodal lines that I put through that are still symmetric. And therefore, when I go to shade in those orbitals, I would simply make sure that I obey the node. So I cross a line, so I have to go here and then there, and then go up here again, and then go back down here, and then go back down there again. Okay? Right? So hopefully that makes sense. Okay? Alright. And then, so that would be an example of one. So we could call this one like psi 3a. And then the other one, I did the first one because that's usually the harder one. But the one that a lot of people come up with on their own pretty easily is you can also have a symmetric two lines by doing straight and straight. Okay? So obviously that is still symmetric, and there are still two nodal lines in there. So I can do this. And it would look like that. And that would be psi 3b. Alright, hopefully that makes sense? I almost asked if that made sense as if you guys are here. None of you guys are here. I'm in my bedroom. Definitely by myself. My roommates are downstairs though, listening to some Zach Bryan something or other. Alright, yeehaw. So that's psi 3a and 3b. Right, and again, we just saw that those have two nodes or two nodal lines. Right? And then, of course, if you want to think about the final molecular orbital, you would have to have 3 nodal lines, and they would still have to be symmetric in here. No, shit. No, I don't want to do that. Okay. And the only way to get 3 nodal lines to cut through this thing and for them to all be symmetric is you have to do this way, and this way. And coincidentally, that winds up being the same as just alternating every single lobe. Yeehaw! And that would be psi 4.
Where you going?
And that's what psi 4 looks like. Yeehaw. Alright, so that would be psi 4. And obviously psi 4 has 3 nodes. Again, 3 nodes, 3 nodal lines, alright? Okay, so the main takeaway, alright? So the first MO has no nodes, right? Meaning all p orbitals are shaded the same. Okay. And then the next energy level has 1 nodal line. And then the one after that would have 2 nodal lines, etc., etc. Okay. The one after that would have to have 3 nodal lines. Alright, perfect. Sweet. Come to my office hours. I don't want to belabor this too much because we're already almost 15 minutes into this video and we haven't even gotten to the fun stuff. We haven't even gotten to the synthetic part. But if this explanation still doesn't make sense, come to my office hours and I can go over it in a little bit more detail with you. But the main thing is that I want you guys to be okay and comfortable with using a frost circle to figure out physically like where the energies of these MOs are. And then you have to use these normal MO rules to then figure out what they look like to actually draw the molecular orbitals. Okay? Alright. But now that we know sort of what benzene looks like and we know about the nomenclature and all of that good stuff, now we can actually talk about reactions. So this is going to be the fun part of this talk. So EAS and NAS. So like I said in the beginning, this is going to be all about how we put stuff on benzene. Alright. So let's get into it. Fun stuff. And we got Raven's Purple. So we're doing so well. Alright. So if you look at a molecule of benzene, okay, and you might say to yourself, well, Brian, benzene looks a lot like... Let me get a much different color. All right. You might say, well, Brian, benzene looks a lot like just a normal alkene, right? So, for example, you might imagine that you had something that looks like this, right? So hopefully you guys remember from Orgo 1 that if you have an alkene and you add something like, HCl to it, then what you will get is this, right? So you might say that this is basically just an alkene in disguise, right? Benzene ring is really just 3 different alkenes in the same molecule. So you might think that if you add HCl to benzene, you might think that you would then do the same exact thing. You would get an H here and a Cl here. Assuming you only did it to one of the double bonds, right? But it turns out that that is not what happens. And it actually turns out that if you just add HCl to benzene, nothing will happen. And the reason that nothing will happen, we kind of already talked about this when we looked at the molecular orbital energy levels of benzene. But again, if you look at these energy levels right here, all of them are much, much, much lower than the 0 point energy. And what that means is that all of the electrons in benzene are very low energy, which means that benzene is a shit nucleophile. It's a shit nucleophile because all of its electrons are stable. They're comfortable, right? They're in a very low energy orbital. They don't need to attack an electrophile because they're content with where they are. Conversely, right, if you look at, so I'll put in, right, benzene has 6, so there's 6 electrons here. Conversely, if you look at the lowest unoccupied molecular orbitals of benzene, so these ones right up here, these ones are substantially higher than the 0 point energy, meaning that benzene's LUMO, or LUMOs, because there's 2 of them, so benzene's benzene's LUMOs, right? Benzene's LUMOs are very high energy, meaning they're unstable. And what that means, just like benzene is a shit nucleophile, benzene is also a shit electrophile. And because it is very, very poorly nucleophilic and very, very poorly electrophilic, that means it's just not very reactive, right? The electrons in benzene are in very stable orbitals, and the antibonding orbitals of benzene are highly unstable, so no nucleophile is going to want to attack it, all right? So therefore, normal reactions that work for alkenes, they don't work for benzene, and if we want to get benzene to do any kind of useful chemistry, we have to do it a very, very particular way, and that is why EAS and NAS are their own little sections, and we don't learn about benzene when we learn about normal alkenes in Orgo 1, okay? Okay, so let's talk about EAS first. So EAS stands for electrophilic aromatic substitution. And in electrophilic aromatic substitution, we are, how do I want to word this? So in electrophilic aromatic substitution, benzene is the nucleophile. And I just told you that benzene was a very shit nucleophile. So the only way the EAS will work is if we use an extremely hot, okay? And in organic chemistry, they use the term hot. It just means very, very good. So we use an extremely hot electrophile, okay? So the typical electrophiles that you guys are used to, something like HCl or HBr or HI, or like an alkyl halide, those are not going to be hot enough. You have to go balls to the wall if you're going to get something like benzene to react with it, okay? So we have to use extremely, extremely hot electrophiles. And it turns out that the way to do this, almost always, is we use these things called Lewis acids. And Lewis acids are capable, the reason we use them, Lewis acids are capable of turning, you're gonna be so proud of me, I'm gonna use some Gen Z lingo. It's capable of turning a mid electrophile, super mid, absolutely no Riz, capable of turning a mid electrophile into a hot. Capable of turning a mid electrophile into a hot electrophile, and that's why we use Lewis acids, okay? So how do you know what a Lewis acid is? Okay, so Lewis acids, okay, they're one of 2 types, okay? They are either metal cations, so something like iron, 3 plus, or zinc 2 plus, or copper 2 plus, etc. So they're either metal cations or they're incomplete octets. So incomplete octet nonmetals. And if you remember from your Gen Chem days, the atoms that have incomplete octets are the ones in group 2 and 3. We don't really ever use group 2 because they would be a little bit too unstable. But we use group 3. So that would be like boron and aluminum. So boron and aluminum both only have 3 bonds when they're neutral. Only have 3 bonds in their neutral state. So when you have something like AlCl3, AlCl3 is neutral. However, it has a giant empty p orbital. And as you might imagine, because electrons live in orbitals, if you have an empty p orbital, that is the equivalent of offering free rent to somebody that is homeless. And there's no shot that those electrons in any kind of molecule would not jump at the opportunity to live in a free orbital, right? Okay. So AlCl3 has an empty p orbital. Again, boron also only has 3 bonds. So if you have something like a really common one is like Bf3. So if you have like Bf3, there's a giant empty p orbital right there. And that giant empty p orbital is what makes Bf3 very good at taking electron density from something, at taking electron lone pairs from something. All right. So that is how to identify a Lewis acid. All right. So now that you know what a Lewis acid is, okay, we can talk a little bit more about how to do some EAS reactions. All right. So the EAS general strategy, and then we're going to get into the mechanism after we talk about the general strategy. But the first step is make the hot electrophile. That's always going to be the first step. And the way that you make the hot electrophile is by using a Lewis acid plus the mid electrophile. Okay? That is always going to be the first step. The second step, benzene is going to attack the hot electrophile. So step 2, benzene attacks. Rah! Alright. And then step 3, always the final step, you are going to deprotonate to restore aromaticity. Deprotonate to restore aromaticity. Alrighty. Yeehaw. So, with all of that said, it took us an hour to get there, but we can now get into the actual fun stuff. So let's say I have benzene, and my boss says, Brian, the cure to cancer is if you are able to create chlorobenzene. Okay? And I say, how do I do that? Well, it turns out that there's a really easy way to do that, and that is by simply using Cl2 and a Lewis acid. And usually the Lewis acid that we use for this will be AlCl3. Okay? Alright? So let's take a look at why this works mechanistically. So the first step of the reaction is to form the hot electrophile. Okay. So chlorine has a lone pair, and the lone pair is going to go into the empty orbital of AlCl3. That's going to get me to okay. Now, aluminum normally only wants 3 bonds. Aluminum now has 4, so aluminum is neutral. And chlorine normally only wants 1 bond, and it has 2, so chlorine is now positive. Okay? All right. Remember, guys, get good at formal charges so that you can understand. So I'll do this example just so that nobody is confused. So if I were to actually put in all of the lone pairs and everything on this, then it would look like this, okay? So chlorine, if you have a periodic table, chlorine is in group 7 on the periodic table. So chlorine wants 7 electrons. Right now it has 1, 2, 3, 4. A bond only counts as 1, so 5, 6. So chlorine wants 7, it has 6, therefore chlorine is positive. Aluminum is in group 3. Remember, a bond counts as 1 electron, so it's going to be 1, 2, 3, 4. So aluminum wants 3 and it has 4, therefore aluminum is negative. Okay? Again, get good at formal charge so that you can do that rapidly in your head and that you don't have to really think about it and do it for every single step of every single mechanism. But that gets me to this. Where's my thing? Okay. That gets me to this molecule right here. All right. And this is my hot electrophile. So that's step 1, generating the hot electrophile. And the reason, if you're like, well, Brian, why is that a hot electrophile? What makes that so much more electrophilic than just normal Cl2? So one of the definitions of an electrophile is anything that is connected to a good leaving group. And we know that chlorine is a good leaving group. Okay? So chlorine is a good leaving group. It should make sense. So because chlorine is a good leaving group, if I have Cl2, then Cl2 is electrophilic because if a nucleophile... Oh, shit. Come on. Dude. Oh, my God. If a nucleophile with a lone pair attacks this chlorine, then the leaving group can leave, right? But it should make sense to you that if neutral Cl is a good leaving group, then positively charged chlorine is going to be an absurd leaving group, right? Because now, instead of just Cl neutral, I actually have a positively charged chlorine, right? So now, if I have a nucleophile attack this chlorine, instead of giving electron density to a neutral chlorine, I'm actually giving electron density to a positive chlorine, which would want it even more. So this thing is going to be ridiculously hot. Okay? Ridiculously hot. Okay. So step 1 was forming that hot electrophile. Now step 2 is benzene is going to attack. So nucleophile attacks electrophile, leaving group leaves. Right? So when that happens, that gets me to here. So we're now on step 2 of the reaction, right? So when that happens, that now gets me to here. So all right, sweet. All right, so hopefully everybody can understand that that's what would be the result of the second step. Okay? And then the third step is deprotonate to restore aromaticity. Okay? So I have an H right here. And what's going to happen is that this right here, because this aluminum does not want to be negatively charged, so this aluminum is going to send the electrons in this bond back towards the chlorine so that it can pick up that H, and that bond will go right there. So that the final result will, of course, be I've regenerated my catalyst, and I now have HCl as well as a byproduct. But the main thing is that I now have that. Okay? Does that make sense? Hopefully that makes sense to everybody. All right. So, in summary, if I have a benzene ring and I add Cl2 and some Lewis acid, I will chlorinate my benzene ring. Okay. All right. And that exact same thing will work for bromination as well. So if I use Br2 and a different Lewis acid, I could have also used AlCl3, but in practice, people will use a Lewis acid that has the same counter ion, just so that in case there's any kind of contamination, it doesn't actually introduce a different halogen ion into your system. But the mechanism is going to be exactly the same. Okay. Right. Right. And I can do this with iodide as well. I can use I2 and a Lewis acid. Okay? Alright? So hopefully that makes sense to everybody. Alright? Alright. Let's talk about some other things. Let's say I want to add things onto my benzene ring that are not simply halogen atoms. So another thing that I can add so this is called a sulfonate. So I can add an SO3H group, which is called a sulfonate. And the way that I do that, very, very easy, is I just use H2SO4. And optionally, I can also include SO3. Your professor might tell you to include SO3, but technically you don't need to. If you have concentrated H2SO4, concentrated H2SO4 will produce this anyway, right? So H2SO4 with optionally SO3 will give you this. So again, let's go ahead and actually do the mechanism to think about how this works. So the first step is I'm going to form my hot electrophile. If you notice, in this step, we don't use a Lewis acid. The reason we don't use a Lewis acid here is because sulfuric acid is a strong acid on its own, so we don't need a strong acid and a Lewis acid. We can just use the strong acid. So SO3 looks like this. And H2SO4 is an extremely strong acid, and because H2SO4 is an extremely strong acid, it will protonate right? This can grab that, and I can form this species. And this is my very, very hot electrophile. Alright? So that's how I form my hot electrophile. It's literally just protonating SO3. Okay? And then in step 2, I'll make the different steps different colors. So in step 2, right, I know that benzene attacks my hot electrophile. So, man, oh shit, that's positive. Okay. And that gets me to here. Alright. And then last, but certainly not least, the final step is to deprotonate to restore aromaticity, and coincidentally, you're going to restore the catalyst. So the sulfate anion that I generated will reform sulfuric acid. So that the final molecule is, of course, SO3H. Okay? Perfect. We can keep trucking along. Right? So what if I want to put on a special group? Oh, actually, I forgot. A really interesting thing about putting on it. So you might say, are SO3H groups really relevant? Because I've never heard of them before, and they're not really relevant from an absolute standpoint. They're really relevant synthetically, and probably in like half an hour when I get to that part, I'll tell you why. But it turns out that when you put on an SO3H group, you can actually take off an SO3H group pretty easily. And the way that you remove that, okay, blah, blah, blah. So let me get a different color here. So if you have this, if you use dilute H2SO4, so meaning H2SO4 plus water, you can actually cleave. So obviously you'll replace it with a hydrogen. Most of the time, well, not most of the time, all of the time, hydrogens are implied, so usually you won't see this actually drawn. But dilute H2SO4 will remove the SO3H, and if you are thinking to yourself, well, that seems really stupid, why would we learn how to put something on if we're just going to take it off? I will get into that in a little bit. But for now, just know that if you have H2SO4 with SO3, you can put on an SO3H group. And instead of H2SO4 with SO3, if you have H2SO4 with water, then you can remove that SO3H group that you just put on. And it turns out that doing so is actually pretty important. Okay? Alright. So let's talk about some more things that we can add. So I can also put on a nitro group. So a nitro group is an NO2 group. And the way that I do a nitro group is by a combination of nitric acid and sulfuric acid. Again, there's no Lewis acid here because sulfuric acid is a strong acid on its own. So I don't need a Lewis acid if I'm just going to have a strong Bronsted acid. All right, so let's do this mechanism. Once again, I know that step 1 is forming my hot electrophile. So in this case, right, HNO3 looks like this. Okay, so that is what nitric acid actually looks like. It turns out that sulfuric acid is stronger than nitric acid, and so this is going to sound kind of weird, but because sulfuric acid is stronger than nitric acid, when you mix the two of them together, sulfuric acid can actually protonate nitric acid. All right, and I know again that doesn't normally happen, but sulfuric acid is so strong that even nitric acid can attack it. Right? So that gets me to here. Okay. And then that lone pair can go there, and that can leave. And so I have now generated this thing. And this is my hot electrophile. So that was step 1, generating NO2+. Alright, step 2. Hopefully you guys are getting good at this by now. Step 2 is benzene attacks the hot electrophile. Okay. And of course, step 3. All right. I'm going to regenerate my catalyst. So I'm going to deprotonate to restore aromaticity. Okay. And that, of course, gets me my final product. Right? Sound good? Okay. All right. And you may also have said to yourself, damn, Brian, I'm not sure I've ever seen an NO2. NO2 is actually slightly more synthetically relevant than like SO3H. But the main reason that we talk about being able to introduce NO2 groups is because if you have an NO2 group, and you don't have to know the mechanism for this part, at least I don't think you might, well, we'll go over the mechanism if we really need to. But what you can do with an NO2 group is you can reduce it. So if you throw in zinc metal with HCl, then you can reduce the NO2 group into an amine. Okay? Or specifically, in this case, this is called an aniline. So an aniline just means an amino group on benzene. Okay? So this is a very good way to make aniline. Alright? So, to recap, right? If you have benzene ring, you can use nitric and sulfuric acid to put an NO2 group on there. If you wanted the NO2 group, that's fine, but a lot of times we use an NO2 group so that we can indirectly make an NH2 group. Okay? And if you have the NO2 group there, you can just use zinc with HCl, and it'll reduce it to make the aniline. Okay? Alright? So hopefully that makes sense for everybody. Alright. So, okay. Let's keep going. Let's say we wanted to add a carbon something or other on this thing. So let's say I wanted to add a methyl group on there. Okay. So the way that I add the methyl group is I add, so a methyl is CH3. So what I do is I take what I want to add, which is a CH3, and I add a chlorine or a bromine or an iodide, it doesn't really matter, and I add my Lewis acid. Okay, and that will do that. So again, let's go ahead and do the mechanism for this so that we can understand why it happens like this. Okay, all right, so if I have methyl chloride, it's going to look like that. Again, AlCl3, my lovely Lewis acid with an empty p orbital. So the chlorine lone pair goes into that. Once it goes into that, it generates this thing. Okay. Right? And remember, this is my hot electrophile. So then, step 2 is benzene attacks. So benzene attacks, leaving group leaves. Okay. And then the final step, of course, is that I am going to deprotonate to restore aromaticity. So that the final thing okay, looks like that. Alright? Sound good? Okay, perfect. So this reaction, it's an EAS reaction, but it actually has its own name because it's very, very useful. Obviously, if we can start alkylating benzene rings, So when you add a hydrocarbon chain to a benzene ring, which is what we just did here, this is a reaction that's known as a Friedel, and I don't know if it's I or E first. I'm going to go with IE. I think this is how you spell it. This is called a Friedel-Crafts alkylation. Okay. Alright. But before we go on, Friedel-Crafts alkylation it has a couple caveats to it, and we need to actually talk about those caveats. So Friedel-Crafts alkylation. So if you notice in the example that I did, I added a methyl group onto here. Okay. So Friedel-Crafts alkylation works really well with methyl groups. So if I want to add like a CH3, or I could have added an ethyl group on there. Or I could have added a tertiary group on there. Alright? So those all work really, really well. But it turns out that if I am adding a secondary group, so if I'm trying to add like a secondary hydrocarbon chain, so a secondary hydrocarbon, or a primary that's propyl or higher, this is not going to work. And we need to talk about why that's the case. So let's talk about why that's the case. So if we think about this mechanism, so let's do the first example. Let's think about why this might not work if it was something like, propyl or something. Okay, so the first step we know, right? So for example, you might say to yourself, oh shit. So you might say to yourself, if I have a benzene ring, and if I want to turn that into propyl benzene, right? I should be able to just add propyl chloride with AlCl3. And it would seem like that would work, right? But let's actually do the mechanism for this and think about why that doesn't work. So the first step of the mechanism is I form my hot electrophile, right? So the lone pair goes and attacks the Lewis acid. Okay. That gets me to here, okay? Now what happens here is that this actually breaks off because chlorine does not want to be positively charged, okay? So this will break off. And when it does, then I generate this thing. Okay. And if you notice, this is a primary carbocation, and primary carbocations are extremely, extremely unstable. And so, because they're extremely unstable, they will do a hydride shift. And when they do a hydride shift, I now have a secondary carbocation, and because the secondary carbocation is stable, that is the species that will predominate in solution. And so my benzene will actually attack the secondary position. And because it attacked the secondary position, my overall final product will be this thing, not, okay. Because if you're reading left to right, it would look like I was saying. So it would be this thing. It would not be the actual thing that I wanted, which was that thing. So it would be this, okay? It would not be that, right? And if you're thinking to yourself, well, Brian, why didn't the methyl thing do that, right? You didn't show the methyl group forming a carbocation. Well, I didn't do that because it would form the carbocation, right? So here, right? Let's go back. Okay. So let me. Shit. Okay. So. Okay. So here, right? Even if it did do that, right? And I formed CH3 plus. Okay. CH3 plus can't actually do a hydride shift. So there's nothing, this thing can't rearrange to a more stable carbocation. So therefore, benzene will still just attack the CH3 plus. Okay. So that's why methyl groups are okay. All right. If you think about ethyl, ethyl is the same way. Ethyl can't actually rearrange to something more stable. So if I had an ethyl carbocation would look like that. Obviously, if this thing did a hydride shift, it would just create this, which is exactly the same. So ethyl groups can't shift to a more stable species. That's why ethyl groups are okay with this as well. Okay? And obviously, tertiary groups, they wouldn't want to rearrange because they're already as stable as possible. So if I had something like, like tert butyl chloride, and I reacted it with AlCl3, the chloride would go attack the aluminum, right? And that would get me to here. Obviously, chlorine doesn't want to be positive, so that would go up there. And that would get me to here. Okay, and that carbocation is as stable as it could possibly be, so it's not going to rearrange, and therefore tertiary centers work really well for Friedel-Crafts alkylation as well. Okay, but a secondary is not going to work very well, and a primary is not going to work very well either. Okay, because of the fact that you will get these sort of terrible rearrangements, and so the thing that you're trying to get will not actually be the thing that you wind up getting. So you may be thinking to yourself, well, damn, Brian, that sucks. So I guess if we want propylbenzene, there's no way to get propylbenzene. But you would be wrong. There actually is a way. So let's talk about that way. So it's going to seem like I'm giving you a completely different reaction, and I am. But that's okay because I'm going to tie it back into how to work around Friedel-Crafts alkylations that don't give us what we want. So let's say I start with benzene, and let's say I wanted something like that thing. Okay? So for that, what I'm going to do is add the thing that I want to add, and I'm going to attach a chlorine to it, and then I'm going to use a Lewis acid. All right? So let's do the mechanism for this one. Again, the first step is to form my hot electrophile. Okay. So the lone pair goes into the orbital. Alright, and again, hopefully, my hope is that at this point you guys are getting very, very comfortable with these mechanisms. Alright. So, looks like this, okay. And then again, chlorine does not want to be positive, so this lone pair on the oxygen will swing down, kick that off, and that gets me this really, really interesting looking thing. It's linear, where it's O triple bonded to carbon. Right? So it's going to look like that. Hopefully you guys can convince yourself that that's what you would make. And this is now my hot electrophile. Right? So step 2, of course, as always, is benzene attacks. And actually, before benzene attacks, I just want you to see, when you're looking at this hot electrophile right here, notice that there is no carbocation. Notice that the cation is actually oxygen, and oxygen does not rearrange. Okay, carbon can rearrange via hydride shifts or methyl shifts, but oxygen, this is actually a relatively stable oxygen carbocation. Well, it's not a carbo, but an oxygen cation, an oxycation, right? So this thing does not rearrange. Okay, carbocations rearrange, but oxygen cations do not. Okay, so we'll come back to that, all right? But anyway, right, so step 1, we made the hot electrophile. Step 2 is carbon is going to attack. Okay. And that's going to get me to here. And then last, but certainly not least, we know that I am going to deprotonate to restore aromaticity. So deprotonate to restore aromaticity, such that the final product is called, or not called, but the final product is that thing. Okay? Alright, so this reaction, just like there was Friedel-Crafts alkylation where we added an alkyl group, this reaction where we add an acyl group, so an acyl group is an alkyl chain with a carbonyl on it. Okay. So if I have benzene ring and I want to turn that into a benzene ring with some R group on it, okay. So this reaction in general is called Friedel-Crafts acylation. And it turns out, right, so you may have said to yourself, well, Brian, this molecule looks kind of similar to the propyl molecule that we were trying to synthesize with Friedel-Crafts alkylation, but we couldn't. And it turns out you're right, they are really similar. The only difference is that one has a carbonyl group. And it turns out that you can actually convert the one on the left to the one on the right, which is why Friedel-Crafts acylation becomes very, very important. So the way that you do this is with something called a Clemenson reduction. Or another way to do this, if you don't want to do a Clemenson reduction, is you can do something called a Wolff-Kirschner reduction. These are just the two scientists that discovered this. Okay. But they both do the exact same thing. One of them is acidic and one of them is basic, so you would just pick one if you preferred to be working in basic or acidic conditions for whatever reason. So a Clemenson reduction is a zinc-mercury amalgam. You don't have to know what an amalgam means. It's a mixture of zinc and mercury, but it's a zinc-mercury amalgam with hydrochloric acid and a shit ton of heat. Okay, you have to make this very, very hot. And then a Wolff-Kirschner reduction is a special molecule, which is just two NH2 groups linked together with potassium hydroxide, water, and also a shit ton of heat. Okay? But that will allow you to get the actual alkyl chain that you initially wanted. Alright? So, with all of that said, right? So, right, we already talked about, if you have a benzene ring and you want to directly put on, something like, let's say you wanted to put on, I don't know, 1, 2, 3, a butyl chain, right? You could not do it this way. Okay, so if you tried to do it that way, this would fail, right? And we talked about why it would fail. The carbocation intermediate that you would form would rearrange. But what you instead could do, okay, so you could instead, if the target molecule was the butyl benzene up top, right, put the acyl version on first, and then just do a Clemmensen reduction or Wolff-Kirschner reduction, right? So I got my zinc mercury amalgam with HCl and a lot of heat. Okay, right? So how would I put on the acyl version? Well, I would just do a Friedel-Crafts acylation, right? And we talked about that already. Okay. So hopefully that makes sense. All right. Good. Perfect. All right. Okay, good. So now I just want to review all of the amazing things that we can now do because of EAS. Okay. So if I have a benzene ring, I can turn that into a chlorine. So I can put a chlorine atom on a benzene ring. I can put a bromine atom on. Let's see what else. I can put on an iodide. I can put on an SO3H group. Okay. I can put on an NO2 group. Once I have the NO2 group on, I can then quickly turn that into an NH2 group. Okay. I can directly put on something like a methyl group. I can also put on an acyl group. Right? And then because of the acyl group, I can indirectly put on longer groups besides just methyl and ethyl. Oh, jeez, thank you. Sorry. Perfect. And I'm trying to think if I'm missing anything. I don't think I'm missing any important ones that you guys would need to know how to put on. Okay, good. And we talked about the mechanism for how to do all of them. So this should make you fairly happy, right? You can put on a whole wealth of groups because of this, okay? And that is all with EAS. But it turns out that we are actually still not done talking about EAS because so far we've only talked about putting stuff on benzene. And the great thing about putting stuff on benzene is it's very easy because we don't have to consider anything else. So when I have a molecule of benzene, this molecule is entirely symmetric. So all of these carbon atoms that I'm highlighting in pink, they're all the same. So it doesn't matter where I put my group, it's going to be the correct answer, okay? But I want you to imagine that I started off with not benzene. Okay, I wanted you to imagine I started off with this sort of ether derivative of benzene. Okay. So now, what do you guys think would happen if I did Cl2 and AlCl3? Okay. Right? What would happen? Well, we know that if I have normal benzene, right? If I just have benzene and I do Cl2 with AlCl3, I know that that is going to put chlorine on the benzene ring, right? We've already done that. But the problem is now I need to think about where exactly that chlorine is going to go, right? Is the chlorine going to go ortho to the thing? Perhaps the chlorine is going to go meta to it. Or perhaps the chlorine is going to go para to it. Right? So which of these options is it going to be? Okay? So we have to talk about how to think about that. All right? All right. Okay. So if you recall, all right, when we were talking about nomenclature, we talked about positional nomenclature on benzene. So if I have my benzene molecule and I have something already on the ring, it doesn't matter what it is, okay? So doesn't matter what it is, all right? So there are ortho positions, meta positions, and a para position, all right? And it turns out that depending on what you have on the ring, what you have on the ring is going to control where the shit that you're adding goes onto the ring, okay? So it doesn't, what you're adding has no effect on where it goes on the ring. It's entirely dictated by what is already on the ring, okay? And the way that we talk about that, all right, is we mention that groups have certain things called directing effects. Okay. So let's talk about those directing effects for EAS reactions. Okay. So there's two types. So the first type are ortho and para directors. Okay. So ortho and para directors. So ortho and para directors they can donate electron density into the ring. And they can donate the electron density into the ring via resonance or hyperconjugation. Okay. And if you guys don't remember what hyperconjugation is just... Oh, shit. Sorry. Hyperconjugation is just resonance. Well, okay, I shouldn't say it's resonance. It's like fake resonance. Fake resonance where you break single bonds. Because normally in resonance you can't break single bonds. But in hyperconjugation you can kind of sort of break them. Okay? So you donate electron density into the ring via resonance or hyperconjugation. And what that means is that your ortho-para directors are either hydrocarbons or anything with a lone pair. Anything with a lone pair. Because obviously if I have a lone pair, I can resonate it into the ring. And hydrocarbons, they have no lone pair, but they can do it via hyperconjugation. So what does that mean? What does that look like? Well, obviously oxygen is going to have a lone pair. So like an OH group or like an ether. Sulfur and nitrogen also have lone pairs. So SH group or like a thioether or a sulfide. Amines or anilines, right? Okay. Halogens have lone pairs. Okay. Alright, so all of these guys, every single one of these species has a lone pair. And because it has a lone pair, it can donate density into the ring. So I'll do it for one of them. So I'll do it for the NH2 portion. So that lone pair can go down here, and that double bond can, for example, go up there. And when it does that, I get a resonance structure. And hopefully you guys can see that that resonance structure looks like this, right? Okay. So again, all of the green ones are going to be orthopara-directors because they have lone pairs, and then even though it doesn't have a lone pair, hydrocarbons are also orthopara-directors because of hyperconjugation, right? And again, hyperconjugation basically means this is not an actual valid resonance structure, but you can imagine that I essentially go like this, okay? And this is not a real, I'm going to put these in in quotation marks because it's not real. But I would get sort of a fake resonance structure that looks like this. Oh, shit. Wait, why did it... Sorry, technology, not my forte. Okay, so if I... So again, this is not a real resonance structure. Hydrocarbons do not spontaneously just split off into H plus and carbon ions. But you can think of this, you can essentially think of the carbon-hydrogen bond as being slightly weakened because it can partially donate into the ring, okay? So if that is too confusing for you, don't worry too much about it. Just hydrocarbons are electron donating groups. They're orthopara-directors. They're very, very weak orthopara-directors, but they still are orthopara-directors, okay? All right. All right. So let's talk about why they are orthopara-directors. Why does being able to donate electron density into the ring cause you to be an orthopara-director? And this is actually really easy to... Oh, shit. What the flying fuck? All right, sorry. Like I said, I haven't done this a whole lot, so... All right, sorry. Hopefully it doesn't do that again. Although that was pretty quick fix. All right. If I have a general... So I'll do another ether. All right. So let's do the resonance structures for this lone pair, right? So where does this lone pair actually end up, right? Well, it ends up on that carbon right there. Okay. And then that could go there, and that could go there. So... Yeehaw. Okay. And then one more. So that one pair goes over there. Okay. So what I want you guys to see is that when you have an electron donor, right, when you have something with a lone pair, it's pushing electron density into the ring, but it doesn't push electron density equally over all 6 carbons. If you notice, and you can do this via the resonance structures, the carbons that actually get the electron density are the 2 ortho positions and the para position. If you notice, the meta position, right? So I'll do the meta in purple. The meta position, right? These 2 positions that I'm highlighting in purple, the meta position never actually gets that carbanion, right? The meta position never gets the carbanion. The only positions that actually get the carbanion are the ortho and the para positions, okay? And if you remember, in EAS, benzene is the nucleophile. So if benzene is the nucleophile, then the more nucleophilic parts of benzene, will be the parts that react. And it should make sense to you that when you're talking about nucleophiles, right, the more negative, right, the more negative a nucleophile is, the more reactive it is. Right? And so when you have something with a lone pair, when you have an electron donor, it increases the electron density on the ortho and the para positions, but it doesn't increase the electron density on the meta positions. So it doesn't increase the reactivity on the meta positions, but it enhances the reactivity on the ortho para positions, and that's why... Oh, come on, what are you doing? Make it what the hell? Sorry. Alright, good. And that is why if I have an electron donating group already on the ring, it is going to favor ortho-para substitution. And so the result would be that my chlorine is going to go para. Or maybe a little bit goes ortho. Normally, it's ortho and para, but normally para predominates unless you have like a very, very bulky group near the para, and then it'll go ortho. Okay, but it would be something like that. All right? All right? Cool. Okay, so we talked about ortho-para directors, so let's talk about the second kind. So the second kind of directors, obviously, would be the only position that we haven't mentioned yet, which would be the meta. So the meta directors. Okay. All right. So the meta directors, they can pull out electron density from the ring via resonance or induction. And if you guys are confused about induction, remember induction just means large differences in electronegativity or how positive something is or how charged something is, but you should think about it in terms of positivity, how positive something is. Okay. All right. Okay, so what do we mean by that? Well, so again, so the NO2, and for this one it helps to know what NO2 like actually looks like. So NO2 looks like this. Okay. So NO2, SO3H, and SO3H. Okay. So NO2. Dude, come on. Sorry. This thing is freezing on me. I'm trying to get it to add a page. Add the damn page, dude. Come on. Alright, well, I'll just have to draw small. Acyl groups. Okay. Some other groups that we'll eventually talk about. So cyano groups. So cyano groups look like this. Ah, shit. Come on. Come on. Alright. Alright, hold on, give me 1 second, because I need to figure out how to add a new page, and this thing's not letting me add a page. Dude, come on. Alright, now it let me add a lot. Okay. Alright, so cyanogroups look like this. Alright, so if you notice, right, the electron withdrawing groups, right, so the NO2 and the SO3H and the acyl and the CN, they all have pi bonds that are adjacent to the ring, okay? So double bond O, right, S double bond O, N double bond O, C double bond O, or C triple bond N, they all have pi bonds. That is going to be the dead giveaway that something is an electron withdrawing group, right? Because, right, if I have benzene, right, I can draw a resonance structure where electron density gets pulled out of the benzene ring. Okay, right? So that is why they are withdrawing, okay? And obviously, so all of these examples, so the NO2, the SO3H, the acyl group, and the CN, they are electron withdrawing metadirectors because of resonance, but you can also have induction. So examples of induction, or examples of things that pull electron density out of the ring just because they're very electronegative, that would be if you have like a CF3, because fluorine is very, very negative. So CF3, or if you have like a positively charged atom, so this usually happens with like nitrogen, so you'll get like positively charged nitrogen, okay? But obviously if nitrogen is positively charged, it's going to just be sucking electrons up kind of like a vacuum. CF3, fluorine is extremely electronegative, it's just sucking electrons up like a vacuum, alright? So it's pulling electron density out that way, okay? Alright, so once again, we should ask ourselves, we should be able to rationalize why electron withdrawing groups are metadirectors. And again, we can do that by looking at the actual resonance structures. So if I have benzene, right, we already did the first resonance structure of this. Okay. Right, so this is positive, okay, and then obviously this can resonate multiple times. Yep. Okay, so when you're analyzing the resonance, hopefully what you guys can see is that when you have an electron withdrawing group, the ortho and the para positions become positively charged, meaning that when you have an electron withdrawing group, the ortho and para positions become less reactive, because again, benzene is going to be the nucleophile in EAS reactions, and if you're a nucleophile and I'm making you more positive, you're going to be less reactive, because nucleophiles want to be negatively charged if they're going to be a strong nucleophile. So ortho and para becomes less reactive, therefore, right, the meta positions will attack the electrophile first. Okay? Alright? So hopefully that all makes sense to you. Alright, so there's one other tiny little thing that we should talk about, and that is So we talked about when you have groups on the benzene ring, it determines where other groups will go. So those are called directing effects. So there's other effects that are called kinetic effects. So kinetic, or some people will call these activating effects. And that just refers to whether or not a group will make EAS reactions faster or slower. Okay. So when you have, so it should make sense, hopefully, that when you have let me draw in all of these. Right, so if you remember when we had all of our lone pair groups on here. Okay, so when you have electron donating groups, obviously if the group is donating electron density into the ring, it should make sense to you that that is going to make the ring more nucleophilic. And if the ring is more nucleophilic, it should make these reactions faster. Because again, in EAS reactions, benzene is the nucleophile. Nucleophiles are more reactive if they're more electron rich. And so therefore, if I'm donating electron density into the ring, I'm going to speed up these reactions. So these are electron donating groups. And electron donating groups increase the reaction speed. Okay. Meaning they are activators. Okay. And likewise, all of the meta-directing groups, all of the electron withdrawing groups, they are going to pull electron density out of the ring. And because they're pulling electron density out of the ring, they're going to make the ring less nucleophilic. And because the ring is less nucleophilic, it will be deactivated. Okay. Right. So all of these, okay, so all electron withdrawing groups deactivate. Okay. They deactivate the ring. Oh shit. They deactivate the ring, so they decrease the speed of EAS reactions. Okay, and again, it should make sense to you. EAS reactions rely on benzene's ability to be a nucleophile. Nucleophiles need electrons. So if I'm taking electrons away from benzene, I am deactivating it. I'm decreasing its ability to perform EAS reactions. Okay, now you may have noticed that I sort of conspicuously left out one very important electron donating group. So halogens, so things like chlorine, bromine, or iodine, even though this thing can donate electrons via resonance, it is actually a deactivator. So chlorine, bromine, and iodide. Okay. Deactivator, even though it is ortho-para-directing. Right? And the reason is because it turns out that the electronegativity of chlorine and bromine and iodine is more important than the fact that it can donate via resonance. And you kind of just have to, that's sort of one of those facts of the universe that I'm telling you and you have to just believe me. it turns out that that's true, right? There's not really too much of a rhyme or a reason for that, but it turns out that the electronegativity of chlorine and bromine and iodine outweighs those atoms' ability to donate their lone pairs via resonance. They can donate their lone pairs via resonance, which is why they're OP directing, but it turns out that they're so electronegative that the amount of electrons that they pull out ends up outweighing the electrons that they can donate via resonance. And so therefore, halogens are the only exception to the main rule that donating groups are activators and orthopair directors, and withdrawing groups are going to be meta-directors. Okay, so all withdrawing groups are meta-directors. Okay, so if we want to summarize, okay, so if it's an electron withdrawing group, it will always be a meta-director. So electron withdrawing groups will always be a meta-director and a deactivator. So meta-director, any electron withdrawing group is a meta-director plus a deactivator. Okay. Electron donating groups besides halogens will be ortho-para directors and activators. And then the only rule breaker is that halogens are ortho-para directors but deactivators. Okay, halogens are the only example, right? So it should be pretty easy. Just know that halogens are the only example of the rule breakers, and then remember the general rule: if it's a withdrawing group, it is always going to be a meta-director and deactivate the ring. And if it's a donating group, it is always going to be an ortho-para director and activate the ring. If it's a halogen, it is going to be an ortho-para director, but it's going to deactivate the ring. Whew. All right, good. Perfect. Alrighty. Okay, so let's talk about some downsides. But I'm going to put these in quotation marks because they're not really downsides, because there's ways to get around them. So there's a couple downsides to EAS reactions, and specifically specific types of EAS reactions. But let's talk about them. So a lot of downsides happen when you're trying to do Friedel-Crafts alkylation. Okay. But all of these are fixable. Now, we've already talked about the first one, which is that you can't do primary chains longer than ethyl, or otherwise you'll get a rearrangement. But we've already talked about the fix to that, and I'm going to re-talk about it once I talk about the second problem. The other thing is that with Friedel-Crafts alkylation, you over-alkylate a lot of the times. So if you're thinking, well, what do you mean by over-alkylate, Brian? Well, I told you that you could do, so if you had benzene ring and you added methyl chloride to this with AlCl3, methyl chloride can't rearrange, so I said that this would be a really good way to make methyl benzene. And it turns out that I wasn't trying to be mean, but I was kind of sort of fibbing to you when I said that, because if you notice, methyl benzene with this methyl group right here, methyl benzene is going to be a more reactive, right? Because hydrocarbons, we already talked about this, hydrocarbons are electron donating groups. And because the hydrocarbon is an electron donating group, methylbenzene is more reactive than benzene. So the moment that I make methylbenzene is going to react with any excess methyl chloride faster than benzene, and I'm going to wind up putting another molecule on that, another methyl group on there. And then once I have two methyl groups on there, it's going to be even more activated. So then this one is going to react even faster, right? And I'm going to put, it's going to go orthopara, right? So, I might put it there, right? And and now this one is even more reactive, right? So this one's going to react. And before you know it, I have a polyalkylated product, which I don't want, right? So if you ask yourself, well, how can I avoid this? Well, the way to avoid this is the same way that we avoided number one. And that is, we do an acylation first, and then reduce to the alkylated product. Okay. So let's talk about why that would work, right? So if I started off with benzene and I wanted only monomethylbenzene, right? I don't want to get hexamethylbenzene. I don't want 6 methyl groups on there. I want to be able to stop at 1, right? So what I could do, right, because I know I'm not going to be able to do that in one step, but what I can do is I can first put on that, right? And this is an electron withdrawing group. And because it's in a withdrawing group, it's actually a deactivator. And because it's a deactivator, I don't have to worry about this molecule in the pink. I don't have to worry about it accidentally reacting with, let's say, I don't know, let's say I wanted to turn this into propylbenzene, right? Right? I don't have to worry about this molecule in the pink overreacting because it's actually going to be less reactive. So I'm stuck here. And then once I'm stuck here, I can then simply do my favorite either Clemenson or Wolff-Kirschner reduction. I'll do a Clemenson because it's easier for me to remember that one. It's a zinc mercury amalgam with HCl and a lot of heat. Okay. Right? And that allows me to selectively get just the monoalkylated product, right? Again, if I didn't do it this way, if I tried to just do it, well, first of all, I would rearrange if I did it the other way. But even if I didn't rearrange, if I tried to just sort of brute force do this via alkylation, every single time I alkylated, it would become more reactive, and it would just lead to more and more and more alkylation. Okay, so I'm not gonna attempt to do it that way. If you want to monoalkylate something, monoacylate it first, which is very easy, and then just reduce it. Okay. Okay, so that's one of the downsides to EAS is that Friedel-Crafts alkylation will either rearrange or it'll over-alkylate, but you can fix both of those problems by acylating it first and then reducing it. Okay, so let's talk about another potential downside, but it's not really a downside. It just looks like it might be. Okay, so what if you have competing? Okay, so another potential downside. What if you have competing directing effects? Okay. And so what I mean by that is, let's say you were doing a reaction and you had, let's say you had like an ethyl group right there, and an ether right there, and you were going to put on, let's do Cl2, AlCl3. So you're going to put on a chlorine, right? Okay, so we know that we're going to put on a chlorine. So we have to think, should we put, if you look at this, right, both of the groups on the ring are orthopara directors, okay? But the problem is that the orthopara for the methyl group, which I'll put in purple, is going to be right here. The oxygen is already on the other ortho position. So right here. So the purple is going to be where the ethyl group is directing. But then the green is going to be where the oxygen is directing, and the oxygen is going to be directing here. And so you might say to yourself, well, crap, which one is going to happen? Well, in this case, it's just determined by the strongest donor. So the strongest donor, so the strongest electron donating, oh shit. Motherfuck, it's doing this thing where it won't let me add a page again. Alright, good. So the strongest electron donating group is going to be, dictates the position, okay? Dictates the overall directing effect. Alright, and it should make sense to you. So how do I know what is the stronger thing, right? Well, so actual lone pairs are way better than fake hyperconjugated lone pairs, right? Meaning hydrocarbons, which don't really have lone pairs to donate, they just do that hyperconjugation, which is like fake resonance. Hydrocarbons are very weakly donating, so actual lone pairs are going to be better than fake hyperconjugative lone pairs, right? Meaning hydrocarbons, i.e. alkyl chains, are very weak donors. They're very, very weak electron donating groups. Okay, so actual lone pairs, okay? And less electronegative is better than more electronegative, okay? Obviously, if I want to donate electron density into the ring, if I have a very electronegative element, the definition of electronegativity is that I don't want to share electrons. So, for example, if I had like an ether and an amide, right? Oxygen is more electronegative than nitrogen. Therefore, nitrogen is more willing to donate its electron density into the ring than oxygen is. Therefore, nitrogen is going to be what determines the overall directing group. And so this would actually direct towards the pink, not the oxygen, because nitrogen is less electronegative. And then the final thing is that resonance... Well, I'll keep it so that everything is flowing in the same direction. So no resonance is going to be a stronger donator than resonance. And that should make sense to you as well. If something is resonating, I should say no resonance besides the ring, obviously. No resonance besides the ring, and then resonance besides the ring. Okay. So for example, right, if I have an oxygen up here, and I have another oxygen, but the top oxygen can resonate into the ring, and the oxygen on the top right, it could technically also resonate into the carbonyl. So the oxygen on the right is not going to be dumping as much electron density as the one on the top because it's splitting its time by going into the carbonyl. And so therefore, the strongest donating group is going to be the top oxygen, and so this is going to direct to the pink. Okay? Right? So hopefully those rules make sense to you. And I just want to point out, it is always the strongest electron donating group. It is never the strongest electron withdrawing group. So if you have a very strong withdrawing group and a very strong donor group, it'll still be the donor group that wins out. If you have a very strong withdrawing group and even like a weak donating group, it will still be the weak donating group that wins out. It's always the strongest donating group that wins. Withdrawing groups will never outweigh a donating group. Okay? Never, ever, ever. Okay? Um, so if you want like an example of that, right, that would be, let's say you have an NO2 group right here, and let's see, the NO2 group normally would want to go meta. So let's say you also had like an oxygen group right here. Okay. So the NO2 group in green, let me make the NO2 group a different color. So the NO2 group, which is in, the NO2 group, which is in red, so that wants to direct right here. And the oxygen group wants to direct either here or here. All right. Now, the NO2 group is a very, very, very good withdrawing group, and oxygen has a lone pair, and it doesn't have any resonance, so it's a pretty decent donating group. It turns out that the donating group outweighs the withdrawing group, and therefore, this will actually donate, or not donate, it'll direct at the purple positions, and this molecule will not direct at the red positions. Okay? So hopefully that makes sense. All right. Okay, and then we kind of already talked about this, but the final little thing that we sometimes have to worry about is for ortho-para directors. So obviously it's ortho and para, and you might say, well, which one is it? Do I go ortho? Do I go para? Does it not matter? So for steric reasons, para is almost always preferred. So para is usually preferred. Okay. But ortho is preferred. So ortho can be preferred if there is a bulky group. So ortho is preferred if there is a bulky group nearby the para position. Okay. So, for example, right, like if you have this dumb thing. Okay, there we go. So, for example, right, like if you have a so let's say you have a big giant tert butyl group here, and this one right here, and you added Cl2 and AlCl3. Okay. So here there's essentially two options for where you could put this chlorine. You're going to wind up putting the chlorine here. Okay. And that's because it's closer to this methyl group. You would not put the chlorine here because it would be very close to this massive tert butyl group. Okay. So hopefully that makes sense. Another way that this sometimes comes up is that if you, again, when you're doing this, just always try to think about sterics, right? So let's say you have a group here and a group here, right? And you were doing Cl2, AlCl3, right? So what you're not going to do, okay, so, well, I'll say what you could do first. You would put the chlorine right here. Oh, shit, sorry. Nope, you wouldn't do that. That doesn't even make sense. Where's the eraser? Okay. You're going to put the chlorine right here, all right? You would not, the chlorine would not go ortho to both of them because, again, that would be the most sterically encumbering situation. Okay. All right. So those examples are pretty few and far between. All right. But just know that usually para is preferred unless putting it para, forces you to be close to a very large group. Okay. All right, and then lastly, okay, if I have a strong deactivator on the ring, so something like an NO2 group. NO2 is very, very, very withdrawing. So this molecule right here would be strongly deactivating. So strongly deactivating. And it turns out that this molecule right here is so deactivating that if I tried to do a Friedel-Crafts alkylation on here, right? So for example, if I had this benzene molecule and I tried to do, right, even a Friedel-Crafts that normally would work. So like this one with AlCl3, right? If I tried to do that one on here, it wouldn't work because it turns out that carbocations are decently hot, but it turns out that even this electrophile this electrophile is still not hot enough to react with it's still not able to react with this. And that is because this molecule is extremely non-reactive, okay? So this is only the case with Friedel-Crafts alkylation, because the hot electrophile in Friedel-Crafts alkylation is actually like the least hot of all of the electrophiles. So nitrobenzene can still do, pretty much all of the other reactions in EAS, but nitrobenzene is not going to be able to do Friedel-Crafts alkylation because it's simply not reactive enough. And then I lied. There's actually one more that I have to talk about. The sort of thing that you have to consider is when you're working with anilines. So anilines are actually really reactive because nitrogen is not very electronegative. So anilines will speed up the reaction tremendously. But anilines, they're also basic, right? So that lone pair can grab a proton if there's a nearby proton. So if you have aniline and you're trying to do, so if you have aniline right here, and you're trying to nitrate the aniline, right? So you're trying to make this molecule on paper, right? You might think that would work really well. So you're going to throw in nitric acid and sulfuric acid. But the problem is that nitric acid and sulfuric acid are just going to protonate your aniline, right? And when that happens, you're just going to get a protonated anilinium salt, right? Like that. And that is going to be extremely unreactive, okay? Very, very, right? Because now this is actually an electron withdrawing group because it's a positively charged nitrogen. So it's going to act like a vacuum and siphon all of those electrons out. So this is now very unreactive. So you cannot do this either. All right? Okay? Hopefully that makes sense. All right? Perfect. Okay, so we're already 2 hours and 20 minutes in. I didn't realize that this video was going to take me this long to do. We haven't even gotten to NAS reactions, but I'm going to take a break and then I'll make a separate video for NAS reactions. But hopefully this helps you and this made sense to you. Go back and rewatch some of these sections if I went too fast in them. But I did do all of the mechanisms for them. And hopefully you guys understood the logic. Like I said, when I finish taking my break, I'll do a section on NAS. And then I'll also, once we do EAS and NAS, and you can add basically anything that you would want to add to benzene, we'll do some practice problems that I'll work through with you. So, yeehaw. And yeah, give me like half an hour and then I'll upload that NAS video.